Hello everyone, this is Miss Dowd here to talk to you more about electrons. Now yesterday or maybe the day before for some of you, you started to learn about electrons in Bohr notation. Today we're moving on to talk about electron configuration, specifically the orbital diagram electron configuration. So this is going to be also called arrow notation, and you'll see why in a moment. So we talked about how first that the atoms have electrons, then we discussed how these electrons are in energy levels, but we're going to take that one step further. So the energy levels are the locations of those electrons, and it's solely based on their energy, which we talked about is based on their period number. And the higher the number, the higher the period, which means the higher the energy, therefore they're less stable. Just a general trend throughout the world, throughout chemistry, is that the higher energy decreases stability. So each energy level has sublevels called orbitals. So orbitals is a word you're going to be hearing a lot. So orbitals is the energy level. The energy level has its sublevels called orbitals. I would suggest writing that down because this is called orbital notation. So within those orbitals, all of the electrons have the same energy. And another way to describe these orbitals is the most probable location for an electron. As we know, electrons have very little mass, and electrons move very quickly, so it's difficult to really know where they are at any given moment, but the orbital tells us approximately where they are. So here we have four different types of orbitals. We have S, P, D, and F. Also, I would write this down, S, P, D, and F. There's one S orbital per energy level at every energy level. S is in every energy level, and there's just two S electrons per energy level. Next, we have three P orbitals per energy level, starting at the second energy level. So there's no 1p, but we start at 2p. After that, we have 5 d orbitals per energy level, starting with the third energy level. So there's no 1d or 2d, but there is a 3d orbital. And as you probably guessed, for the f orbitals, we start with the fourth energy level. So there's no 1f, there's no 2f, there's no 3f, but there is a 4f energy level. So s, which is the lowest energy level orbital, is at all levels. P starts at energy level 2, D starts at energy level 3, and F starts at energy level 4. And I'll show you how you memorize this with the periodic table, so it'll be a lot easier to think about. All right, so we knew this. So each orbital can fit these two electrons. So since there's only one s orbital, it only holds two electrons. With the three p orbitals, each one of these p's holds two electrons. So we have 2 plus 2 plus 2 to give us a total of 6 electrons. So at each energy level, the p orbitals can hold 6 electrons. Then we move up to the 5d orbitals. So we have 2 plus 2 plus 2 plus 2 plus 2, otherwise known as 2 times 5, and we get 10 electrons within those orbitals. And finally, we have 7 f orbitals, so 2 times 7 gives us 14. So that's how many electrons each one of these orbitals can hold. They won't always hold that many, but we'll be able to discuss that in one moment. They have these unique shapes, which you see here. So here, these s orbitals are sphere shaped, so they get, at each energy level, they just get bigger and bigger spheres. The p orbitals look like these dumbbells or the infinity symbol. The d orbitals have a couple different shapes, but the ones pictured here kind of look like two peas put together or like a flower. And then the f orbitals just kind of go crazy a little. So that's why they're the highest energy level, because there's so many different spots the electron can be. So these different orbitals show us where the electrons are most likely to be. So if they're in an s orbital, they're most likely to be somewhere in this sphere. Okay, here is a picture you've seen before. You saw this in the quizzes lesson, and I just wanted to highlight it because it really illustrates to you how you know where the s, p, d, and f electrons are. So on the periodic table, this would be hydrogen, and then this is helium. So this is your s block. So all of these are your s electrons. Remember, there's only two s electrons, so of course it's going to be the part in the periodic table where there's only two elements right next to each other. We move over here, we have our p electrons. We know there can be 6, so there's 1, 2, 3, 4, 5, 6 different elements lined up next to each other here. Here we have our d orbital, or sorry, our d block, which is where the d orbitals live. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then finally our F, which has 14. So this, I think, is the easier way to memorize this, and you'll just get the hang of it. But I just wanted to show you this diagram. Okay, so now let's look at carbon. So we know that carbon has an atomic number of 6. So how many electrons does it have? Yes, carbon has 6 electrons. Awesome. So that means we have to fill our orbital diagram. So I'm going to first show you the correct one and then some incorrect ones. So here we have an orbital diagram. We have 1s, our lowest energy level orbital, then 2s, then 2p. So 6 electrons means we need 6 arrows. So each electron is represented by an arrow. We have one down, then one up, then one down, then one up. So that's 4 electrons. And then we need 2 more. Let me show you some incorrect examples. So here's one where we only have 1 electron in this 2s orbital, which is wrong. Here's one where they're too close together. And then finally here, we know that orbitals can only hold 2 electrons, so this is too full. This cannot hold 3 electrons. So here's one example of a correct orbital diagram and 3 of an incorrect one. So let's talk about the different rules we have for orbital filling principles. First, we must always start at the 1s energy level and work our way up. So we always need to start from low energy and work our way up to higher energy. Next, we need to fill all empty orbitals at a given energy level before pairing up. For example, if you're filling the p orbital, you need to fill 1 in each p spot, so px, py, pz, before you can double any up. And finally, each orbital can only hold 2 electrons, only 2. So here, in our third example, some of them had 3 arrows in it, 3 electrons, so that was incorrect. Let's look at another example. So lithium. Neutral lithium has 3 electrons. And we're going to start with our lower energy level. So we put 1 arrow in there. Remember, we need to fill our empty orbitals at the same energy level first. And then we need one last arrow to give us a 1, 2, 3 for our 3 electrons. And we know we can only hold 2 electrons here. So this is our correct orbital diagram for lithium. Next, let's look at oxygen. So this is atomic number 8. So we have 8 electrons this time. 8 electrons. So first we're going to start with our lower energy level. So down 1, up 1. We want to fill that first. Then we move on to 2s. Then afterwards, remember, we want to fill the 2p one by one, and then we can start pairing up. How many arrows do we have here? We have 8. So this is our final diagram for oxygen. So here we have to make sure we followed all the rules, and it looks like we did. All right, our next objective is evaluating orbital diagrams based on the 3 filling principles. So we have to make sure we're following the rules. So our 3 filling principles have already been introduced to you. First, we know that we have to fill from low to high energy. That is called the Aufbau principle. Next, we know that electrons fill empty orbitals at given energy levels before pairing. This is called Hund's rule. Hund's rule. And each orbital can only hold 2 electrons. This is called the Pauli exclusion principle. Please take a moment and write these down. Orbital diagrams. And we have to decide, using those 3 rules we just wrote down, why they are incorrect. Which rule is violated? So for this first one, please take a moment and think about those 3 rules and think about which rule was violated in this instance. Now, if you guess that it violates the Aufbau principle, you'd be right. And it's because it did not fill the lowest energy level first. Here we went 1s, 2s, and then we skipped filling this energy level to go up to 2p. So this is incorrect because of that rule. Next, let's look at this second example here. This second example. Which rule do you think is broken here? If you decided that this one violates Hund's rule, you'd be correct. Hund's rule states that it needs to fill those empty orbitals first before pairing up. Here we see that these 2 arrows are put in the same orbital before spreading out. So we need to make sure that these arrows are separated. And finally, this last one violates the Pauli exclusion principle because it has too many arrows in each box. So that is the end of our presentation today, talking about electron configurations with orbital diagrams, and you'll get some more practice in after this.